All right, good morning and afternoon, evening, everyone. Thank you for joining us today and welcome to the DAS RCN webinar on applications of distributed acoustic sensing for monitoring and verifying geological storage of CO2. I am Casey Adderhold, speaking from the Incorporated Research Institutions for Seismology headquarters in Washington, D.C. IRIS is a consortium of universities and an NSF-funded science facility operating programs that enable Earth scientists to perform advanced research in geophysics, particularly in seismology. This webinar will be recorded and archived on the IRIS Earthquake Science Presentations webinar YouTube channel. Should you have a comment or question as the webinar unfolds, then please clearly and concisely type it into the Q&A box, not the chat box, on your Zoom control panel. At the end, we will read your name and question to the presenters. If similar questions have been asked, we may combine or skip them. If the webinar happens to crash due to Zoom or internet issues, we will reboot it. Just click the webinar link again. Use of distributed acoustic sensing is rapidly expanding in our community, prompting the initiation of a research coordination network to facilitate workshops, tutorials, and other opportunities for sharing ideas and resources. This is one in a planned series of webinars on different topics within distributed acoustic sensing. I'm going to pass this to Dr. David Eaton now to introduce our speaker today and moderate this webinar.
Well, thank you, Casey, and many thanks to IRIS for this opportunity to give a webinar. It's my pleasure to introduce the main speaker for today, Dr. Don Lawton, who's a professor emeritus of geophysics at the University of Calgary, and also a director for the Containment and Monitoring Institute, part of the CMC Institutes. Dr. Lawton's research interests include geological storage of CO2, as well as acquisition, processing, and interpretation of multi-component and conventional seismic data, and near-surface geophysical studies for environmental applications. We'll also have part of the presentation given by Dr. Jan Dettmer, who's been a faculty member in the Department of Geoscience since 2016. He was an ONR postdoctoral fellow in 2007 and 2008, and subsequently held research positions at the University of Victoria and Australian National University. His research interests include seismology and acoustics, and particularly earthquake sources, earth structure, and inverse problems. So I will pass things over to Don Lawton to get started with the webinar.
Thanks very much, Dave. So I'll share my screen and move into the main presentation here. Just want to confirm that the screen is visible.
Yep, looks good.
All right, well, good morning, evening, afternoon, everyone. Very pleased to be able to present to you today on some aspects of the application for DAS, as Casey mentioned, for CCS, carbon capture and storage. It's really a very fast developing field as everybody in the world is looking at emissions reductions, and this is one technology that can really, in the short to intermediate term, satisfy those goals, or at least work toward those goals. So we'll do just a little bit of background for those who might not be that familiar with CCS. Why is it needed? And then some of the drivers for implementing it. Then what are the monitoring requirements and how DAS plays a role in that. And then we'll do a virtual tour from a video of our field site. We have a small field station in southern Alberta where we're doing CO2 injection and monitoring. And we'll share some examples of data from that site, and Dave will have some from other applications of DAS for monitoring as well. So a reminder that what's driving the whole issue about climate change is increasing CO2, atmospheric CO2 concentration, now averaging around 410 ppm, and you see from this graph the very dramatic increase in CO2 concentration over the past 100 years, and the realization that this is really tied to global temperatures. And there are various diagrams you've seen like this, which is emissions reductions pathways. I'll just bring my mouse into view here and make my pointer visible. So our business as usual shows increasing emissions. We're currently around 30 gigatons per year, but in order to get the below 2 degree scenario, we need to follow this blue trajectory, and this big green wedge here has a variety of technologies that can be used to reduce those emissions. What's really important to remember is that in order to get to what we now call net zero by 2050, even by the end of the century, we'll need to actually go to negative emissions, and I'll talk about that as we go on. So there's various technologies in here, including carbon capture and storage to meet these goals. So what is CCS? Essentially, it's capturing CO2 from either stationary or large emitters, or from distributed emitters, or even now from the air as an option. And there are really three aspects of utilization and storage. One is conversion, turning CO2 into useful products, shown by this part of the graph. And then utilization, we're very familiar with carbonated food and beverages, but the big use for utilization here is in enhanced oil recovery. And that itself has discussions about whether or not using CO2 for EOR is just adding to the problem or reducing it. And then storage is what we'll talk about today. We capture it in the pipeline or truck to a site and inject into a deep storage horizon. Of these, conversion probably can only take about 3% of the total CO2 available in terms of market pool, and utilization is probably somewhere around possibly 10%. So we really have to be addressing storage as a way to rapidly reduce emissions. And I mentioned negative emissions. There are various companies now like Climeworks in Switzerland, Carbon Engineering here in BC and Canada, who are now looking at direct air capture of CO2 from the air. And if we then inject and store that underground, it really would be a true negative emissions, which is where we need to get to by 2030, probably is the current modeling, as one of the storage vectors from direct air capture. This is the wedge chart from the International Energy Agency that I'm sure most people are familiar with. So these are the various wedges that make up the total reductions for the 2-degree scenario. Efficiency around 40%, renewables 35%, and carbon capture and storage currently estimated to be about a 14% of that contribution, which seems like a small wedge, but in reality, this places it at around 5 gigatons of CO2 being stored through CCS by 2050, and that's a large volume. So we need all these different emissions reduction vectors to get to where we need to be in emissions reductions. So CO2 storage is simple in concept. We have a capture facility, perhaps at a power station or other sort of industrial facility. We transport it by pipeline to a certain location, and we drill a well and store it deep underground in a formation that A, has room for it, and B, has the appropriate sealing rock so that the CO2 will not want to migrate up section, because it is a buoyant gas, even in supercritical state. So typically the depths will be anywhere greater than 1.5 kilometers, so CO2 will be in supercritical state, which is some of a combination between a fluid and a gas in terms of its physical properties, but it is the dense phase or the most efficient way to store CO2. So there's certainly opportunities for large-scale storage around the world, and the various types of reservoirs or formations that it can be stored in is shown in this cartoon. I mentioned already enhanced oil recovery and enhanced gas recovery from coal, but really the key ones are depleted oil and gas reservoirs, which are usually under pressurized, and that the original pressure can be returned by injecting CO2 into those reservoirs. But the biggest opportunity is really in these deep saline aquifers. And there's good examples in North America where this is now being taking place. I'll refer to one of them later in the talk. So around the world, this is a map compiled by the Global CCS Institute. There's at least 19 large-scale projects. You see many of them in the US, several now in Canada, but developing elsewhere around the world. This one off the coast of Australia, the Gorgon project, is actually CO2 out of natural gas fields, and that CO2 is being extracted from the gas production and re-injected by Chevron and partners, and that's around 5 million tons a year, I believe, is the target which they started last year. Storage capacity has also been estimated by a large number of groups, and these just show some of the storage potential. Here in Canada, we're sitting at somewhere between 200 and 430 gigatons storage potentials. I believe it's now been increased significantly above that. The US, 2,000 to 21,000 gigatons. So you can see in Europe, Southeast Asia, there's lots of storage potential available for injecting CO2 as an emissions reduction technology. So here in Western Canada, I'll just refer to some local aspects. We have the Alberta Basin sitting here in the dark green. This is basically a map of the western part of Canada. And these are the best storage opportunities because we want to be storing, if we look at the phase diagram of CO2, pressure on the y-axis, temperature on the x-axis, we want to be above the critical point. So if we're injecting around 2 to 2.5 kilometers, such as the Shell Crest project, we are well into the supercritical phase of CO2 injection. And then as we move to different parts of the basin into Saskatchewan, the depth of the storage formation gets a bit shallower, so the storage volumes become a little less. But we can store many gigatons here in the Alberta Basin. So what are the drivers needed to accelerate it? One is we need firm climate policy to meet the Paris Accord, and this will be coming up again in Glasgow at COP26 in October this year. Regulation, and what industry needs is certainty. That's one of the issues is lack of certainty in the regulatory environment for emissions reductions. But on the investment side, companies are looking at ESG ratings. This is environmental, social, and governance ratings for investment opportunities, and the environmental aspects are primarily focused on CO2 storage. We hear this phrase net zero carbon by 2050, now by over 200 companies worldwide. So that's a goal to get to. Already talked about investment. There's really an increase in interest in hydrogen, in particular in this part of the world here, blue hydrogen, which is making hydrogen from natural gas as a feedstock, which has a large carbon footprint. So we need to deal with that. And then on the monitoring side, a lot of technology development, including DAS, which we'll talk about here this morning. And then how do we do this at a cost-effective manner? So that's also a key part of it. So in Alberta here, back in 2013, the CCS regulatory environment was very well established. It's probably one of the leading policy groups in the world. So we now have this carbon sequestration tenure regulation, which is designed to enable large-scale projects to hand environmental liability back to the government after an assessment period post-closure. So that's very important for uptake for industry to consider. In terms of the life cycle of a CCS project, this is the slide I borrowed from Schlumberger. We go from site selection, characterization, design. Otherwise, is that site suitable for storage? The construction, both subsurface and topside, preparation, and then start the CO2 injection. And that's where we want to be doing continuous or semi-continuous monitoring through to the injection phase, ultimately then decommissioning, and then surveillance post-closure for a period to ensure that the CO2 is stable in its location. And that requires really technologies to be developed for MMV, which is measurement, monitoring, verification, and the appropriate closure plan. So we want to be monitoring really from the injection zone through to the atmosphere, all of those different parts of the geosphere. So as part of this, we wanted to get out of the lab and out of numerical modeling these types of opportunities and going to the field. So we were fortunate being able to set up a field facility in southern Alberta. It's about 200 kilometers southeast of Calgary, where we had access to around 400 hectares of land that we could install this monitoring site. And the goals here was to develop the site for validation of MMV and develop new ones for CO2 containment and conformance, and really looking at being able to rapidly assess leakage if there was a containment problem in a deep storage reservoir? And can we quantify the CO2 detection threshold below surface? If we wait till CO2 gets to the surface or the atmosphere, then it's a little late for leakage detection. So we want to look at that at the depth we're injecting at, in this case, which is around 300 meters. And then use that technologies, particularly things like DAS, to really develop surveillance technologies for the cap rock and the overburden section in general. This is the picture of our site, and you'll get a video tour of that shortly. And on the right is the footprint of our site. It's 1 kilometer by 1 kilometer in terms of the active area. The background grid is our active source baseline. The red dot in the middle is our CO2 injector well, and the 2 green dots are observation wells that we have at the site with different types of monitoring systems in those wells, and then a broad range of surface monitoring technologies that I won't talk about here today. The black squares are broadband seismometers. Mike Kendall has been working with us on those for the past 5 years. So again, the goal is to consider opportunities, or if there was leakage from a deep storage zone shown in this cartoon, if gas migrated up section and then flowed into a shallow aquifer, could we detect that before it gets to surface? So that's really the modus operandi of why we set up this site. And then, so what we're doing is directly injecting at the shallow depth rather than waiting for a leakage path. So if it was here, we detect it. We work with a large number of different groups and collaborators on all aspects of this project. You can see the people here, really an international consortium of researchers working both from atmospheric monitoring to the shallow subsurface to the reservoir level. So we're very fortunate of being able to work with a large international group at our site. And what we'll focus on now is the opportunity for using distributed acoustic sensing, or DAS. So we have installed this fiber loop shown in the right part of this diagram, and I'll explain this in more detail during the video. So it's just a quick intro here that we have a 5 kilometer loop that's in both observation wells and also along buried in a trench to look at the opportunities for surface seismic measurements. Fiber is shown here by the hammer. The thick cable, this is a particular geometric design of fiber, helical wound to try to improve the directivity function of DAS, because as we know, the DAS fiber is sensitive only to longitudinal strain. So the idea is can we design different geometries that would give more omnidirectional response of DAS in seismic monitoring. So I'll now, hopefully the video will run here. It's about a 12-minute video, which is a tour of the site and some of the aspects of it.
Hi everybody, my name is Greg Maidment. We're out in Newell County at our field research station for Carbon Management Canada, CMC. This facility was really brought together by Dr. Don Lawton. It started as a place to show CO2 injection best practices, but it's really turned into a world-leading research center for monitoring as well as CO2 injection. The purpose for us here now is to be able to combine as many different monitoring data sets to come up with a very comprehensive picture of what's happening in the subsurface. We've got surface seismic, downhole seismic, fiber optics throughout the whole facility, over 5 kilometers of fiber optics, as well as all of our monitoring equipment on the surface and down our injection wells. We've also been really lucky with not only the ability to be gifted all this technology for subsurface monitoring, but we've also become a world leader in emission monitoring as well. We've got one of only 2 dual cone mass spectrometers on site, which measures a live 3D image of all emissions passing through the site, so that we can combine that subsurface monitoring with anything that's moving up through the atmosphere. So we'll have a quick walk around. I'll show you everything at the facility and give you a little tour on how operations happen here at CMC. So we're in our control shack. Our full facility can be run and controlled from this computer, which we are lucky enough to be able to remotely log into from Calgary. All of our recording devices that are in the facility run through this computer, and then our other recording devices, the ERT, fiber optics, geophones that are downhole, the geodes, are all run from inside the classroom. So one of the main goals of the FRS, of the Field Research Station here, is information dissemination, sharing of information, collaboration, and general learnings around the process. So we have an on-site classroom to work through. You can see our second CO2 monitor sitting here, just for safety along the site. Inside the Appl trailer here, we have a classroom for learning, for teaching, for working, as well as our technical room on the end here, which has all of our computer systems in it, the controls for the dual cone mass spectrometer, for the geodes, for the ERT, and any of our weather stations as well. So we have our CO2 tank behind us here. Currently we truck our CO2 into site. It's stored in liquid phase in this large tank here. It holds about 52,000 kilograms. To keep it all in liquid phase, we have our cooling towers behind it. Pushes the gas phase gas up one side, gas phase CO2 up one side, pushes it over at the heat exchanger on the top, and as it falls down the other side, it compresses into liquid CO2 so that we keep the pressure low in the tank and we don't have to deal with any explosive issues. So our CO2 stored in liquid phase comes down through our piping into our pump. Our pump pulls it out of the tank. We've got a variety of gauges, both temperature, pressure, as it comes out of the tank, and our emergency ESDs to shut down the equipment. The pump keeps it in liquid phase and pushes it down the pipeline to our next heater. So after we pull the liquid CO2 through all the piping, we bring it to this heater to turn it into gas phase. So the heater can heat the gas up to about 200 degrees Celsius. It's much easier to inject. Injected into the reservoir below. So this is our Christmas tree. This is our wellhead. The CO2's come along through this pipe. It's now in gas phase, and then it's injected into the production tubing downhole into the Basil Belly River, our reservoir of interest. We have quite a few different gauges on the wellhead to measure, again, pressure, temperature, downhole, as well as that surface. And one of our CO2 monitors here, we can see we're currently at 240 ppm at this device. This is one of our safety shut-off features in case we have a leak out of the wellbore. This is our geophysics observation well. We're only 20 meters away from the injection well. Down this hole we have geodes around the injection zone, as well as two different fiber optic loops, one of them helical wound and one straight, so that we can observe any sort of temperature changes through DTS, any acoustic changes through the geophones and the DAS. This is our second observation well. We call it the Geochem well. We're 30 meters away from the injection well now. We have open screens at a variety of reservoirs downhole so that we can actually take samples of gases that are moving through, liquids that are moving through the reservoirs, bring them up to surface for testing. So in conjunction with the subsurface injection and monitoring, we're also doing emission monitoring. So we have a dummy tank that we're using here to do methane releases from. We have a controlled amount of methane that's released from our dummy tank. Use the tank as the background for OGI cameras, for laser-based recording, as well as the dual cone mass spectrometer and any drone or airplane basis that comes and wants to test their technology. For this full cycle monitoring program, we have quite a few soil sampling sites all over the section of land that we're operating on. We also have quite a few water sampling wells at a whole bunch of different depths. So we can measure how the aquifer changes from 150 meters all the way up to surface. We've seen no changes. We wouldn't expect any changes, but we need to make sure that that's the case, and we need to see if there's any subsurface variations. So this is U of C's recorder behind us here that is doing operations in conjunction with the Vibe out in the field. We're collaborating with the U of C on all of our surface active seismic. So we can see Malcolm operating the U of C Vibe in the background there, and just to the left of him, you can see that dirt line, which is part of our trench that has our over 5 kilometer long fiber optic loop. We have a down and back in each direction for a full kilometer of fiber optics buried in the ground, and then it goes in and out of all of our wells. So on top of our down hole recording and our trench of fiber optics, we also have a continuous hawk system that's buried underground, that's reading for passive signals. It's reading for any sort of microseismic, any shifts, any changes in the subsurface. So we have a large array permanently laid out, taking these recordings, and we update them every month.
Hi, I'm Don Lawton. I'm the director of CAMI within CMC, working with Greg and all the other group here, and we're today looking at the installation of DAS at our field site that you've seen on the tour with Greg. And we're specifically interested in using DAS as a monitoring technology. And at the site here, if you can see the screen here, we have a 5 kilometer loop of DAS optical fiber. We're sitting in here in the shack, and the loop goes out, and we have 2 observation wells, and we have DAS fiber, 2 types of fiber in observation well number 2, a helical wound fiber, which is shown in blue, and a regular straight fiber shown in green. So it goes twice into this well, goes across into the second observation well, and then the loop goes into a kilometer-long trench, and we have the straight fiber and the helical fiber in the horizontal trench here as well. So we're looking at using the optical fiber for VSP measurements and surveys in the observation wells, which we're currently doing today. To look at the time-lapse response, the injector well, not shown on this diagram, but it sits between these 2 observation wells. So we're doing walkway VSPs and walk-around VSPs into these 2 wells. Here today is a time-lapse monitoring for tracking the CO2 that we're injecting from the inject well. And as well, we're looking at the responsive fiber for surface seismic acquisition to record both reflections. And we've been working a lot on surface wave analysis, looking at the surface wave modes that Jan Dettmer will talk about as a means of characterizing the near surface and looking at time-lapse variations in that as well. So from here, we'll look quickly at the interrogator, then we'll go outside and just look at how we connect these fiber loops together. Okay, so think back to the loop diagram we just saw. So this is the real-time display, waterfall display of all of the 5 kilometer fiber that we have. Remember, it goes twice in observation well number 1. So this first section is the helical fiber in observation well number 2. This is the straight fiber in observation well number 2, then the straight fiber in observation well number 1. And then we have a split. This is the straight fiber in the trench. This whole section is the 1 kilometer long helical wound fiber in the trench, and then the second half of the straight fiber in the trench. So we can, in real time, monitor the whole 5 kilometers on this display. But this will be recorded continuously while we do this VSP survey that is running here today. And then we'll be leaving this interrogator running so we can capture passive seismic events, particularly in the wells, as we're injecting CO2, as Greg showed you from the injector well description earlier on. So we're now outside at one of the junction boxes. It looks very busy, but here the fiber coming from the office is split into fibers running into the trench and into the wells. Each of the black cables is a bunch of fiber optic lines. You see where I'm pointing to now, there are 4 color-coded fibers coming out of one of the black cables. Each of those is a separate loop, so we have lots of redundancy. And it's really critical when you're doing the splices, which are held on by the red tape on the backboard, that the splices are done very well, because we often get significant signal loss through the splices. But this was done very well, and we've been very satisfied with the performance of the box. You can see the fibers blowing around in the wind. They would actually induce noise, so that's why we keep this box sealed and closed whenever we're operating the system.
Hello, my name is Eaton. I'm currently working as a postdoc researcher at the University of Calgary, and Don Lawton is my supervisor here. So my project here will relate to the time-lapse dots data site, which is acquired at the CAMI site, and I will also use the Interrogator for my research.
Hi, I'm Marie Maquet. I'm a geophysicist working at CCS RCN Institute. I'm mainly focusing on geophysical methods, so ERT and seismic data. And what I'm doing with the DAS is record continuous seismic data and to try to see how we can characterize the effect of the CO2 injection on the subsurface. So either if we can detect any microseismicity due to CO2 injection, or if we can image the CO2 propagation. One of the challenges we have with the DAS is it's a lot of data. We have 5 kilometers of fiber on the site, and it's gonna be close to 2 terabytes of data every day. So we have to come up with a plan to try to work efficiently with this data, either by applying some machine learning data algorithm method to try to process those data as fast as we can, and not having to keep 2 terabytes of data per day.
All right, well, I'm back. I just want to confirm that I'm still online. If somebody could confirm.
Yes, you are.
Okay, so that's kind of a tour of the site. So this Dave, Jan, and I, and another couple of UFC researchers are fortunate enough to actually have purchased our own interrogator. It's an OptoSense interrogator. This just on the left side just shows our machine room. This is the interrogator sitting in here, and all the other equipment. This is the ERT system down here, and downhole geophones are being monitored here. So all this is accessible over the internet from Calgary, so it's really good. This picture on the right you already saw. I worked on it through the video, but each of the red cones here is the mini-vibe, actually a sweep of mini-vibe. So time increases from right to left here. So you can see the sweeps of the mini-vibe being captured on both the VSP and surface seismic surface loops of the DAS. This is a 1 meter upward trace spacing from the interrogator. So there's 5,000 traces per record. We capture many records per hour. So on the left side here of these three from the VSP data. So the first arrivals right up at early times here. This is 0 to 4 seconds. And you can, when you zero in, you really see nice upcoming reflections, which I'll show you in a minute. There's the helical fiber, the straight fiber, and observal number 2. This is observal number 1. And then the right-hand side here, all of the data from the surface trench. And what we see, it's dominated by surface waves, and Jan will talk about some of the modal analysis for later on, which is great because at this trace spacing, we have unaliased surface waves, which really is a powerful additive for this type of work. If we just now zoom in on some of the VSP data, this is now being separated into the upgoing wave field measured on the DAS. Over the depth of the well. In this case, the well's 320 meters deep, so it's 0 to 300 from left to right, and we see all these beautiful upcoming reflections recorded on the DAS. So we've been very pleased with the performance here, and this really provides broadband data for us to do monitoring. So we're repeating these VSP surveys now every couple of months, and we've been injecting now for 2 years, and we're just getting to the stage now where we have enough CO2 in the ground that we think we'll better start imaging it with seismic data. And this is a process section, a comparison of a walkaway DAS section here on the right. So we image out to 98 meters from the well. The well's here at the boundary between these two sections. So we have geophones downhole as well, but over a more limited vertical aperture, only from 190 to 305 meters, whereas the DAS goes from surface to bottom hole. So one immediate advantage of the DAS is that we are able to record on the full depth of the well, which is really a powerful addition. but you can see how well these events track between the geophones and DAS. Of course, we're measuring different things. DAS, we're measuring strain rate in this case. Geophones are measuring velocity. So there are conversions in order to So DAS imaging for VSP is being used by other projects, and in Alberta here, the Shell and part of the Quest project has now been running for 4 years. They're injecting 1.1 million tons a year at a depth of 2.3 kilometers in a unit known as the basal Cambrian sand. And it's a very good storage reservoir. We think it's capable of gigaton storage, but Shell is recording yearly VSP walkway VSP surveys, and you can see an example here of a time-lapse response between 2015, 2016, and the difference here at the reservoir zone. So you're able to map the CO2 plume with DAS. So we're just about at this stage now at our insight of being able to look at the time-lapse response. So what I'll do now is talk about some of the, or I'll pass over to Jan Dettmer to talk about some of the other components that we're working on at the site. So I'll pass over to Jan if you want to come in, Jan.
Yeah, sounds good. So I just turned my my mic on here. Hopefully it's loud and clear. Yeah, so as Don was saying, there's really a great opportunity, I think, at the site in terms of the wealth and diversity of data sets that are available and for research. And this is really just some early work that is scratching the surface of what will be possible, I think. And so what I'll be talking about is some of the inversion work that Lu Peng Q has done. She's a PhD student at the Cruise Consortium at U of C and has worked on these surface wave data. So on this first slide, what you see is the cable or fiber geometry in the top left-hand corner here under A. And so we have several hundred meters of DAS data that are being used, and you can also see some the observation wells and the location of the source. So the source in this case was the vibro size with I think a 16-second sweep from 1 to 150 hertz frequency content. And in the middle panel, you can see the time domain data recorded on the DAS, and we're comparing in the top row the DAS recording to co-located geophone recordings. We then process these data just with simple FTAN processing into this representation on the right-hand side, which for those initiated, they would immediately see that these are modes for Rayleigh waves in this case. Why do I say Rayleigh waves? Because we're locating the source in line with the fiber, so we have mostly signal propagating along the fiber, so as to not having to worry about some of the directionality limitations of DAS. Of course, it's not guaranteed that there could be some love wave energy in this as well, but we're working under the assumption that these are Rayleigh waves. What's really nice in this figure is I think you can see some of the overtones very clearly in this data set, and when we're comparing that to geophones, we see some issues, in particular that in this case, the geophones are higher in frequency cutoff, so we can't recover some of the lower frequency information, and there's also some evidence of aliasing. So if we go to the next slide, this is the data that we extracted from the rightmost column on the previous slide. And what we're comparing here is essentially two inversions. On the leftmost panel is a fundamental mode inversion, which is probably the most typical type of data to extract from many surveys where we would be limited to geophone data. And then with the DAS data, we were able to extract these higher order modes. and we applied then a Bayesian inversion algorithm to this, and the color code or coded background here is a bit hard to see, but it's essentially what we would call in inversion jargon the posterior predictive probability. It's essentially how well the inversion is able to fit the observed data, and what we can see is that there's very good agreement, and we're sort of further exploring this on the right-hand column just by demonstrating that the residual of observed minus best fit data is largely uncorrelated. That's one of the things you want to pay attention to when you're evaluating inversion misfits. And so if we go to the next slide, it summarizes the inversion results from this study, where we applied was sometimes referred to as a transdimensional Bayesian inversion. That this just means that we're treating the number of subsurface layers as unknown, so as to not having to make subjective choices about these things. On the left-hand side, we see the inversion result of the fundamental mode. So this is an image of the S-wave velocity as a function of depth down to 120 meters. The color code refers to the sort of dark blue colors are low probability, and then the lighter colors are high probability. So we can see if we follow these high probability peaks, that is sort of where the preferred solution would lie for this inversion result, and we're quantifying the uncertainty. As we include additional modes, we can really see that we improve resolution in the shallow-most parts of this model. This is new information that was gained from these DAS data that wasn't previously available, in part related to some of the limitations of downhole measurements that Dawn mentioned. And we can also see that we dramatically reduce uncertainty, both in the shallow and in the deep parts of the structure. So if we go to the next slide, the same data can also be analyzed with other methods. So this is just a quick example here. I'm going to go through this pretty quick, but we can process the DAS data to represent displacement instead of strain rate, to then apply it in standard full waveform inversion codes. So this is we'll be applying a two-dimensional full waveform inversion here, and we're looking from left to right. It's essentially the processing steps. So we go from strain rate to the displacement, and the rightmost panel just sort of shows a comparison to demonstrate that this is sort of a sensible processing flow. So if we go to the next slide, where we can look at some of the results for this full waveform inversion. So this is a linearized full waveform inversion approach, where we need to start with a starting model that is then iteratively updated by increasingly improving the misfit to the data. So we start with a simple horizontal stratification model in the top right-hand side. And then now we're going almost about 3 times as deep as we looked at before with the surface wave dispersion analysis. And what we see here is that we, in fact, resolve very similar structure, but we can now also detect lateral changes in this model. And we think it's really exciting to be able to resolve these lateral changes as well. And the future work will then consider sort of these time-lapse data sets that Dawn was previously mentioning, to repeat essentially this kind of analysis on data sets that are repetitively collected, and then see if we can detect any changes in the reservoir, which would be about 300 meters depth in this case. So in the last slides, really briefly here, where we can just sort of quickly look by flicking back and forth between these 2 slides to see how this inversion, in fact, improves the misfit to the data. We're comparing the inverted data set with the observed data set, and we're matching the data sets here much better than based on the starting model. And so that's just one of the things that you want to see in these results. Okay, so I'll hand it off there to David, I think.
I'll pass to Dave now.
Great, thank you. So I'll jump in. I'm going to keep my remarks really brief because I want to leave a little bit of time for questions at the end of this 1-hour webinar. But I did want to just say a few things about use of DAS to monitor hydraulic fracturing, which we're not doing at the CAMI site, but we're doing elsewhere in Alberta in partnership with industry operators that we're working with. We collected a few data sets quite recently, but those are in early stages of analysis. So I'm just going to use some results that are published in the literature. Just as a reminder to people here, hydraulic fracturing is a process wherein fluids are injected under sufficiently high pressure in the subsurface to induce fracturing of the rock mass. And in this study that you're looking at, there were 2 wells that were drilled horizontally. So we're looking down in map view. The hydraulic fracturing occurs within a discrete stage along the horizontal well. And the cartoon is showing the fractures that are growing away from the injection well on the left towards the monitoring well on the right. And the monitoring well has a DAS fiber which is cemented into the well outside of the casing. And the waterfall display you can see on the right shows a lot of complexity that I'll explain in a minute. But essentially, colors that are shown in red represent extension, which is measured axially using the DAS fiber on the horizontal well. And areas that are shown in blue represent compression, which is occurring. And below that, there's a graph that shows the pumping rate. And when the pumps are turned off, you see an immediate reversal in polarity. So fractures that were expanding start compressing, and then the area around the fractures starts to relax as well. So if you go to the next slide, Don. So to explain this a little bit more, the example I showed previously was DAS data resampled to 1 second sample rate with an anti-alias filter. And it was showing the strain rate observed axially along the DAS fiber. So this figure is taken from a 2016 paper. It is modeling of strain from a hydraulic fracture. And so you can see the absolute strain with the same color scheme. So compression in blue and extension in red. The fracture itself is symmetrical. So the arrow is showing the fluid injection point. Below that, this has been converted to strain rate. And then to the left in part C, you can see an enlargement where it's clear that most of the action is happening close to the fracture tip. So just off the end of the tip, we're getting extension occurring, and then in a kind of butterfly-shaped pattern adjacent to that, we have compression occurring. So as the fracture tip passes by the optical fiber, it leaves a distinctive signature. So next slide, Don. So the diagram you're looking at right now is a waterfall display, time on the horizontal axis and location along the fiber and the vertical axis from another publication from 2020. Again, you can see in these dashed black lines where individual fractures were characterized using the DAS. And in each case, there's a characteristic extension in red and compression in blue, which represents passage of a fractured tip past the fiber. And then on the right in the white circled region, you can see closure, which is happening after the pumps are turned off. So I think I'll leave it at that to keep things very brief and turn it back to Don to summarize.
All right, thanks, Dave. So this is just an update of what we're doing with DAS at our injection facility, and really reminding ourselves that CCS implementation at a very large scale, gigaton scale, was really necessary to meet the global GHG emissions reductions. There are policy incentives like the 45Q code in the US to entice industry to do this, but we need regulatory changes to increase the uptake. And also working with the public, getting public confidence that this technology is effective, safe, and will enable us to reduce the emissions required over the next 30 years. And of this, on the monitoring side, there's great opportunity, I think, for DAS to monitor any sort of injection program. In this case, we're talking about CCS, but they mentioned hydraulic fracturing. So it's really a powerful technology. And it's another aspect of that is good is because for well completions, you're putting the fiber in on a stainless steel capillary. So it's much less of a risk for well integrity issues than in the past. So that brings us to the end. There are some additional YouTube videos that are available on this link, which shows some of the mechanical aspects of actually installing DAS. It's not as trivial as just running a cable down a hole or in the ground. How you splice it is critical. So there's a list of videos there you're welcome to look at for how we install the current system down at our site, plus some training on DAS setups in general. So that brings us to closure. I want to thank University of Calgary, particularly the Global Research Initiative, who provide a lot of funding for our site and researchers working on it, and CMC who host it. And this is our always, of course, seeking funding. So this is a pots of gold at the end of the rainbow at our site to keep us running here for the next few years. Thank you very much, and I'll stop sharing at this point and hand back to Dave.
Great, well, thank you. I'm going to just go through the questions. We have a number of questions that have been posted to the Q&A. We'll try to get through as many as we can with the time available. I'm not going to mention people's names just to keep things rolling, but the first question is, why do you need both helically wound and straight fibers? So I'll put this one to Don.
We wanted to compare the difference between the two. You would not normally have both in one well, but we really were trying to understand the directivity issues with straight fiber. And that was the reason for installing both. We would not necessarily need both in any situation. So there are lots of research groups around the world looking at fiber design to improve this directivity issue.
Okay, this one will also go to Don, I think, but Jan might want to jump in. It's a two-part question. The first part is, will the snow in winter affect the site and data recording?
Doesn't prevent us from recording. We're used to working at -30 here. So anybody wants to come and visit midwinter, you're welcome. So we do see changes, particularly any of these techniques that examine the near surface. And you saw Marie Mackay in the video. She's working on ambient noise tomography and actually being able to characterize changes in the velocity structure between summer and winter. And I think we'll probably see some of that in the work that Looping is doing with Jan and Chris as well. That will be coming up in the time-lapse work that we do.
Yeah, I can add a comment. I mean, so this is buried fiber. We have seen in other applications that if you have just sort of surface deployed fiber, the snow can make a really big impact on coupling and as well as wind noise. So it can sometimes be an advantage if you had surface deployed fiber.
I'm going to jump around here a little bit, but there's a question here about, do you have any figures showing a microseism recorded with a helical cable compared to a standard fiber?
We've just actually started recording on the DAS box last week, so we haven't actually harvested that data yet. So at this point, we're just recording microseismic events on the geophones, and we have a big surface array as well as the downhole array. We are seeing tens of thousands of events. Some of these are related to human activity at surface, so we're working on algorithms to separate injection-related events from those recorded due to industrial noise at surface. So we're really excited to be harvesting the DAS data actually tomorrow and being able to analyze that, and then we'll be able to answer that question in terms of what we see on the helical fiber versus the straight fiber. So stay in touch.
So I have a couple of questions that relate to the Rayleigh waves. So I'll just kind of combine them here. So the first one is, what is the source of the Rayleigh wave? And then also for the surface wave dispersion, what do you expect would be the deepest range for inversion? And could you extend below 300 meters?
Yeah, so for the data we showed here, the source was a vibe, like a vibro-sized truck. Don can fill in, but I think the signal was 1 to 150 hertz, and on in the processing, we see sort of useful signal to about 3 hertz. So it's an active source survey in this case. And I would say in principle, you can certainly look deeper. You just need to excite surface waves at lower frequencies. So, I mean, there are many surface wave studies that go to greater depths with lower frequencies. The question is just how are you going to excite them? So I'm not sure what the limitations of the VIBE are, but I would expect there could be limitations here, but in principle not. So you would just need a low frequency source.
Yeah, so yeah, the VIBE we are using, the lowest is actually 2 hertz generally, but we've just submitted a paper based on ambient noise tomography, looking at very low frequency surface waves and doing similar analysis to what Jan showed from the fiber. And these were recorded on Geophones. We haven't yet done ambient noise correlation from fiber data. That's upcoming, but we can see less than 1 hertz on the ambient noise tomography, and that gets us down to yeah, we can get just to 300 meters in the work that given the aperture of the surface geophone arrays.
Okay, we're not going to have time to go through every question, but we'll get through as much as we can. There's a question here about how to convert strain rate to displacement and how you deal with the lack of true amplitude when inverting using full waveform inversion.
So I'll pass that to Jan.
Yeah, that's a good question. So I would have to pass those off to Lu Ping for the details of the conversion. I know it's problematic. You have to make assumptions without a doubt. And I saw another question here too that's sort of related to that. So if you sent me an email, we can talk about the deep details on the email about the processing.
Yeah, this is just to add to that. One of the research topics we're looking at is how similar are different interrogators. So at the site, we have tested already 6 different service providers, and some of them measure strain, others measure strain rate. So getting everything into the same units and relative amplitude scaling is still a research challenge. And for applications in 4D or time-lapse, we're finding this is quite difficult, because the time-lapse signals generally are quite subtle. So you need certainty in the instrument response and between different systems to be able to attribute any changes to a true 4D effect and not just differences in instrumentation.
So I think we'll try to wrap things up here. There are a series of questions about the helical fibers. So I guess just to summarize, do you see advantages of using helical fiber? Is it holding up to the promises of theory? Is it a commercial product, and how do you think it performed?
Yes, it is a commercial product. The cable we had is made in Australia. What is interesting is that the response was not as good actually as straight fiber. So we're disappointed in the response. I currently have a PhD student who's really looking at the directivity function. Even though the signal to noise in the helical fiber is lower than in the straight fiber, for a reason which we don't fully understand. We think it's probably due to how the helical fiber was made. It's a one inch diameter rubber mandrel around which you wind the fiber, and then there's a plastic coating on it. So it's potentially just a transfer function inside the cable that is not as good as a conventional straight fiber in a stainless steel pipe.
Last question, just 20 seconds to answer. Are there plans to share data with academia and industry?
Yes, we do operate an industry JRP at the site. We're supported by a number of companies. So data are held for about 1 year, and then we are interested in working with different research groups and making data available. As I showed in the presentation, we have around 22 to 23 international groups already working with us. So we welcome people to come to site, or if there's specific aspects of data analysis that you would like to work on, we can certainly look at working out an agreement to do that.
Well, I think we're out of time now. There are also some questions in the chat, but I'm sorry we didn't have time to get to them. We will take a look at unanswered questions in chat and to the best of our abilities try to respond. But as a reminder, our Don Lawton's email information has been captured in the video and you can see it there. So I will pass it back to Casey and Iris to wrap things up.
Thank you. And thank you to Dr. Lawton, Dr. Dettmer, and Dr. Eaton. The recording will be made available on the IRIS Earthquake Science webinar playlist. If you are interested in future DAS webinars, please join the DAS mailing list and check out the DAS RCN website. Thank you for joining us for this webinar.
Great.